As you saw on that list of topics, this course starts out with some pretty simple stuff. Rather than go through stuff you've already seen and explain it the same way and hope it sinks in, my attitude is either you've seen it once and it made sense and you don't need to see it the same way again, or you didn't understand it and you need to see it differently to make it sink in. Either way, I try to take a little bit different viewpoint on stuff so that maybe if you didn't understand it, or even if you did understand it, you'll understand it a little bit better now. So I try to explain things in a little bit different way than what you may have seen them before. The main thing I try to do different is I try to explain why we do things the way we do instead of just how. Many people will get to this level and they know how to do a lot of math, but they don't necessarily understand why they're doing it that way. And when you get into some more complex problems, trying to solve problems, it's understanding why that helps you figure out and break down that problem and figure out how to deal with it. For example, one concept that I have found that many students don't truly understand, one of the simplest concepts, is the idea of a number. Now you might think, well, that's kind of silly. I've worked with numbers as long as I can remember. I know what a number is. If I put a 4 up here, I'm going to show of hands, how many of you would tell me that that's a number? Most of you would. Some of you realize there's something going on here. So you're being suspicious. 4 is a numeral. It is just an amount. It tells us how much. 4 of something we can count 1, 2, 3, 4. To truly be a number, it not only has to tell us how much, but it needs to tell us of what. Like 4 cows. That is now a number because it tells us how much we have, but then also of what. So we have 4 here, that's the amount. I'm going to refer to that as the count. We can count 4 items there. And then what we have 4 of is the cows. I'm going to refer to that as the name. So 4 cows are the 2 parts of the number. And now it's complete. We have to have the amount and the label. Now, this is not my way of forcing you guys to label everything on your papers. That's not my intention. I don't get real picky about grading that way. But seeing the 2 parts of a number help us to understand how our basic operations interact with each other. So, for example, let's take a look at our 2 most basic operations and how those 2 parts of a number fall into that. So let's talk about addition and multiplication. Now you might be thinking, I thought it was going to be addition and subtraction. Where did subtraction and division go? Well, technically in math, there are only these 2 main operations. Operations come in pairs. Addition and subtraction are a pair. They are really the same operation. Addition is just going forward and subtraction is going in reverse. So any rules that apply for addition also apply to subtraction. And the same relationship goes with multiplication and division. They're the same operation. One's just going forward and the other's going in reverse. So let's take a peek at an example of addition using that count in the name. Let's say we have 4 inches plus 7 inches. What do we get? 11 inches. Good. Probably not groundbreaking information yet, but let's take a look at the count and the name and how they behave. We have counts of 4 and 7. We combined those to make 11. Now we're doing addition here, so we combine them with addition. So when we add the numbers, we combine the counts. Let's look at the names. We had inches and inches, and they stayed as inches. So when we add numbers, we keep the same name. So inches and inches stayed as inches. Well, let's look at multiplication. If I were to multiply 4 inches times 7 inches, first of all, is everybody familiar with the dot being used for multiplication? It means the same thing as the cross. It's just saves space and doesn't get confused with x. 4 inches times 7 inches, what do we get? 28 inches squared. There we go. If you think about it, if we're multiplying 4 inches times 7 inches, chances are we're looking at a rectangle or something. We're trying to find its area. So we do get inches squared. So if we look at what happened here with our count and our name, where our counts are still 4 and 7, and we combined them to get 28. Now this time we were multiplying, so we combined them with multiplication. Either way, we still combine the counts. The difference is in the names. We had inches, and we multiplied them to make inches squared, square inches. When we multiply numbers, we also combine the names. And that's the big difference between multiplication and addition, is when we add, we're going to keep the same name. When we multiply, we're going to also combine the names. Excuse me, this actually has some major consequences. It doesn't seem like a big deal right now, but it has some major consequences in looking at how our other forms of numbers are operating. All those special rules we learned for decimals and fractions and all that stuff actually come from this right here. In fact, this idea even determines what we can even use in each operation. For example, let's say I had 3 cows and 5 boys. If I add them together, do I get 8 cowboys? That doesn't work, does it? Or if I switch them around, 5 boys and 3 cows, would I get 8 boy cows? No. Anybody have the farm background in here? A couple of you? So you can tell me that this is a whole bunch of bull, right? Okay, a long way to go for a joke. But there's a point behind it. When we add numbers, we're going to keep the same name. Well, if we're going to keep the same name, that implies that we had to start with the same name. In fact, that's both addition and subtraction. We must start with the same name because we're going to keep that in our answer. Down here, since we didn't have the same name, we cannot combine those with addition. A little bit more practical of an example might be 3 feet plus 7 pounds. If I go to add 3 feet plus 7 pounds, what do I get? I get 3 feet and 7 pounds. I cannot combine them with addition because they're different units. However, with multiplication, if I had 3 feet times 7 pounds, because I'm going to combine counts, 3 times 7 is 21, and I'm also going to combine the names, feet times pounds is foot pounds. I don't have to have the same name to multiply or divide because I'm going to combine those names. A foot pound is a unit of torque, or if you're looking at structures, a unit of moment. So that is just fine to multiply 2 things with different names. If we look at our other forms of numbers, that explains why we do things the way we do, all those special rules. And we'll go through each of these different forms of numbers in more detail when we talk about them a little more formally. But let's take a look right now at everybody's favorite type of number, fractions. Now you might have noted a little bit of sarcasm in my voice, and I saw a couple of the faces out there when I said that. If I asked students on the way in the door to the class what they hated most about math, about 4 out of 5 would say fractions. The other one would usually say the teacher. Just a little review. The top number of the fraction is called the numerator. Bottom number, denominator. You may have caught me pausing there a little bit. I'll give you a little bit of a heads up. I'm a horrible speller, and I realize my handwriting sometimes gets sloppy too. Um, if anything ever appears up on the board that you can't read, I assure you I intended it to be in English. I either just horribly misspelled it or I just wrote too sloppy. Don't be afraid to ask me what something says. I won't be offended. And a lot of times I'll get halfway through a word like that and forget how to spell it. So be patient with me. Let's look at that numerator and denominator and what they really mean. Numerator, to numerate. Every 10 years, our government sends out people to do the census to numerate the population. What are they trying to do? They're counting. Denominator, to denominate means to, like we have different denominations of organizations, we have different denominations of money. To denominate means to classify or to give a name. So when we look at that 3/7, a lot of people see two separate numbers, but it's not. It is a single number with two parts. Just like having 4 cows or 3 inches or whatever, we have 3/7. Now, when we look at fractions in more detail, we'll define what it means to be a seventh. But for right now, we just need to know that that is a count and a name. And when we go to add fractions, somewhere back in 3rd or 4th grade, when we first learned how to add fractions, that 3rd grade teacher said to add or subtract fractions, you must have a common denominator. That is not a new rule for fractions. Anytime we add numbers, we must have the same name. So now when we add our fractions, we are going to combine the numerators. 3 plus 2 is 5, and keep the common denominator. Very good. Again, that's not a new rule for fractions. Anytime we add numbers, we combine the counts, and we keep the same name. If we were multiplying 3/7 times 2/7, what were we taught to do? Okay, just multiply straight across. Numerator times numerator. 3 times 2 is 6. Denominator times denominator. 7 times 7, 49. Again, that's not a special rule for fractions. When we multiply any number, we combine the counts, and then we also combine the names. Oh, what if we have 1/4 times 3/5 plus 3/5? Can I add those the way they're written? No, they don't have the same name. And to add or subtract, we need the same name. And for fractions, that's a common denominator. Again, when we look at fractions in more detail, we will look at finding common denominators so we can add those. When we multiply, however, 1/4 times 3/5, do we need a common denominator to multiply? No, we don't, because when we multiply, we're also going to combine the names. So just like any other number, we combine the counts. 1 times 3 is 3. Then we also combine the names. 4 times 5 is 20. So there are no special rules for fractions. They're the same rules we use for every other number. They just look different because fractions look different. If we look at decimals, like 0.21. Now, 0.21 is kind of slang. What's the formal way of pronouncing that number? 2100. And when you pronounce it that way, it's pretty obvious that there's a count and a name here. We have 21 of something, and that something is hundreds. So if I were to add 0.21 plus 0.3, is that going to work like that? I have to do what? Yeah, and give them a common name. That's actually very good. We were taught that you have to line up the decimal points. The reason for that is exactly what you said, the common name. This is 21 hundredths. This is 3/10. They don't have the same name. Now, fortunately, with decimals, it's very simple. I just put a 0 there, and now that's 30 hundredths. With that 0 there, the decimal points would automatically line up. Lining up those decimal points in our decimals, is just a way of making sure the numbers have the same name. So then we add 21 and 30 make 51. What do we do with the decimal point? Drop it straight down. When we add or subtract, we keep the same name. Dropping that decimal point straight down means 21 hundredths plus 30 hundredths is 51 hundredths. It's just keeping the same name. A little trickier is multiplication. If I have 0.21 times 0.3, do I need to line up the decimal point when I multiply? No, because when I multiply, I do not need the same name. Well, 21 times 3 is 63. Where does my decimal point go? Okay, I have to put a 0 there and then go 0.063. Why did I have to put a 0 there? Why did it? Okay. We were taught that you count 1, 2, 3 decimal places in the problem. There has to be 1, 2, 3 decimal places in your answer. Well, why? We're back to that 3rd or 4th grade teacher again, right? Because this is 21 hundredths. This is 3/10. And when we multiply numbers, we combine the counts. 21 times 3 is 63. But we also combine the names. Hundredths times tenths is thousandths. So by counting those decimal places in the problem and making sure there are that many decimal places in our answer, what we are doing is combining the names. Well, since we're having fun with this, let's keep going a little bit. Let's look at another type of number, an algebraic number. Now, a lot of textbooks have fancy names for this, like an algebraic expression or an algebraic term. It's really just another number. 4x is just a number with a count and a name. The count is the 4, the name is x. Just like having 4 cows or 4 inches or 4 sevenths, here we have 4 x's. Now the difference is we know what a cow or an inch or a seventh is. We don't necessarily know what x is, but it behaves exactly the same way. 4x plus 7x, what do we get? 11x, exactly. Because when we add, we combine the counts, 4 and 7 make 11, and we keep that same name, so it stays x. If we had been multiplying 4x times 7x, what would we get? 28x squared, very good. When we multiply, we combine the numbers, 4 times 7 is 28, but we also combine the names. So just like inches times inches became inches squared, x times x becomes x squared. If I have 5x plus 2y, what does it become? 5x plus 2y, exactly. Just like when I had the 3 feet plus 7 pounds, it stayed 3 feet and 7 pounds. I cannot combine those with addition or subtraction because they have different names. Same here. However, when I'm multiplying 5x times 2y, what do I get? 10xy, very good. I multiply the counts, 5 times 2 makes 10, and then just like feet times pounds became foot pounds, x times y becomes xy. So it's the exact same rules throughout all of math. They just look different depending on the different types of numbers. Even if we got into scientific notation, you'd have the same thing going on. 5.2 times 10 to the fourth. Here the name is the 10 to the fourth, the power of 10. So if I were going to add numbers in scientific notation, I would have to have the same power of 10, 10 to the fourth and 10 to the fourth. And I would add the counts, 5.2 plus 3.7 is 8.9, and then keep the same name. If I had different powers of 10, just like renaming a fraction, I would have to rename those numbers in scientific notation before I could add or subtract them. If I were multiplying, however, 2.1 times 10 to the seventh times 3.2 times 10 to the fourth. I don't have to have the same name, which means I don't need the same power of 10. Well, 2.1 times 3.2 is 6.72 if I combine the counts, but I'm also going to combine the names. Now we'll go over this in a few weeks. 10 to the seventh times 10 to the fourth is 10 to the 11th. So the same rules apply to all different forms of numbers. Now, as we go through the course here, we'll find that there are more basic operations than what we saw here. We saw addition and subtraction. I said they come in pairs because one reverses the other. We also saw multiplication, and we'll look at its opposite, what's called its inverse, the division. And before we're done this semester, we will see another set of basic operations, powers and roots. Just like addition and subtraction, one is forward, one's reverse. Powers and roots, one is going forward, the other is going in reverse. Those of you in broadband, if you're going for the 2-year and you have to take that second semester math, you'll actually see exponentials and logarithms. Both very big words for concepts that are actually kind of simple, not near as bad as they sound. They're ways of reversing each other. Both groups we'll see in the second semester because we have to work with trig. There's trig functions, and then they're inverse trig functions. All of these are inverses. It's just with trig functions, we're not very creative about naming the inverse. It's just the inverse trig function. So all that is stuff we will see as we go through the next semester. Any questions? Okay, I think that's enough for the first hour. Unfortunately, you guys are stuck with me for 2 hours today. So we will have a second lecture, and there will be a homework assignment today. But rather than to jump right in right now, we've got about 5 minutes left before it would normally. That clock is way behind up there. Are all the clocks in the building that slow? No. I see my computer time here is saying 1:14. So normally we would take a break at 1:20 and come back at 1:30 for the second half of class. So what I'm gonna do is I'll let you guys take about a 15-minute break. We'll come back at 1:30 actual time, not what our clocks are saying here. And we'll start with our second hour of class then.